Kim from Columbia to give today's colloquium. He's going to tell us about one of the most beautiful areas of physics, which is a sole paper by Hofstadter, who thought it was so beautiful and thought things like it were so beautiful. He left physics and wrote books and went into computer science and stuff like that. Philip got his undergraduate degree at Seoul National University. He then got his PhD working with Charlie Marcus on carbon nanotubes. Charlie Lever, sorry. Big mistake. Yes. He's the new Charlie Marcus, is what I should say. With Charlie Lever on carbon nanotubes. He then came to Columbia and he did some really fundamental work on graphene. In particular, and these were the days where you started doing graphene with Scotch tape. But lately he's improved it so you don't need Scotch tape anymore. Discovered the integer quantum Hall effect, later fractional quantum Hall effect. And it was such a clean experiment, and at room temperature even, quantum Hall effect. Such a beautiful experiment. Most of us expected him to win the Nobel Prize for it. But as usual, the Nobel Committee messed up. Okay. On the other hand, this is from Wikipedia, so it must be right. It says, in his Nobel Prize lecture, Andrew Geim, who got the Nobel Prize for this, shared the Nobel Prize in 2010, acknowledged the contribution of Philip, saying, "I owe Philip a great deal for this, and many people heard me saying before and after the Nobel Prize that I would be honored to share it with him." Okay. So since then, he's gotten other prizes. In particular, this year, he's the winner of the Buckley Prize of the American Physical Society, which is the highest prize that the Physical Society has in condensed matter physics.
Well, thank you. Yeah, I probably should check with Andrea whether this is really true. I don't know who wrote these things, but well, so I don't know who wrote these things, but certainly not me. Okay. Well, thank you for coming. Indeed. So I remember that exactly this room. This is my actually second time to coming to. Well, actually, I came here many times, but this is my second time that I come here for colloquium. That first one was about, I think, 6 or 7 years ago. That was a time that graphene research started. A few years. So it was a really beginning part. Many people start kind of pondering around what is graphenes and all this quasi-relativistic quantum mechanics appears in graphene. All this kind of story was discussed back then. And over the time that, of course, there are up and down in any of the research, I would say graphene that was recognized as a Nobel Prize in 2010. Afterward, people start to think that, well, graphene is a good system, interesting system, but it's also a simple system. So maybe things got changed. Is there any more interesting things remain here? I think there are a lot of valid questions here. What I'm going to tell you today is probably not really, really deep physics, but this is certainly one really neat physics and beautiful physics. And also some relatively old problems that recently experimentally got solved. I would say, or shows a kind of great hint that many things can be done in this type of system using the graphene. So that's the story I'm going to share with you. Let me start with thanking my collaborators. Certainly I'm the salesman here that's kind of selling all the work done by the students and postdocs. In particular, Corey Dean, who is now in the City College, did a lot of work here. That basically organizing all the students to work on this field, and they did main part of the experiments as well as the main part of the analysis. The work is in collaboration with 3 different groups, my group as well as Jim Horn and Ken Shepard group, sitting on the same floor of the building, make the kind of synergy of the collaboration. There's strong theory components in here. Pyeongyang Moon and Mikito Kushino and the Tohoku University actually help us to understand a bit of the details of the spectrum I'm going to talk about. And this experiment was done by getting really high quality sample, especially not only graphene, but it's a substrate, serve as the good substrate, which is boron nitride, I'm going to tell you, supplied by our Japanese colleague in the NIMS. All right, story I'm going to tell you today, as my title indicated, there are a couple of names up here, starting from Bloch, Landau, and Hofstadter and Dirac. I'm going to tell you that why actually these names are relevant in my talk. So let me start with the Bloch. Okay, so we know that Bloch did a lot of important work, and one of the most important work is traced back into the 1929, published in 29. This is only 2 or 3 years after Schrödinger published his seminal paper about Schrödinger equations, right? So not surprisingly, around the late 20s, probably many physicists try to find out the interesting example that one can demonstrate as an important solution of Schrödinger equation. What Felix Bloch worked on is that now classical problem, how you can understand electron dynamics in quantum mechanically in the presence of the periodic electric potential, right? And as we all know that once you have the periodic electric potentials, because of this periodic boundary condition, you impose a kind of important structure in the wave function. Now we call the Bloch wave function, contains this free electron like the part as well as atomic part, which is periodic. So that will dictate this the wave function symmetry. A more important part is because of this wave function structure, now your energy spectrum is not continuous anymore, right? Even with a perturbation of this periodic potentials, your energy versus potential relation, energy versus momentum relation of wave electrons in this periodic potentials shows some discontinuous spectrum, right? And if you just consider the periodicity of the lattice, you can fold this spectrum into so-called the Brillouin zone, that what condensed matter physicists often refer, and then you form this kind of discrete band of the energy spectrum, and hence basically the birth of the condensed matter physics started from this point, right? In fact, this Bloch's paper started out this kind of stating this Bloch's theorem, and ends with how the electron dynamics will look like under the presence of the phonon. So this is real kind of big paper, probably serve about 1/3 or even half of the modern condensed matter physics book is in this one paper. So that's kind of amazing things. Now, once you have this spectrum, that there's an interesting integer number you can actually assign, especially when you have a Fermi energy is in the gap of this spectrum. Imagine that I put the Fermi energy in somewhere in the gap. Then immediately what happens is that this energy spectrum, what you call the band, has two different categories, one filled and one unfilled, and completely filled or completely unfilled. Now, because of this symmetry or the periodic boundary condition we have in this system, basically that we can actually count the number of the electrons in here, right? And then the number of the electron in this case, the completely filled band, is just an integer number that filling up each unit cell, which means that always there's one important integer number that we can assign with when the energy is within the gap. Basically, it's pictorially that you can just count how many bands they got filled up in the spectrum, right? And as I said, because this is so deeply tied with number of the electrons per unit cell, there's an easy way that you can also get that number of the filled band, just knowing that electron density up to the Fermi level, where the Fermi level is in the gap, basically this quantity that you just simply take the derivative of the number of the electron density with the unit cell and normalize it again, and this number, dimensionless number, becomes integer that tied with how many bands got filled up, right? So the point I want to make here is when you have this periodic electric potentials in quantum mechanics, basically their naturally integer number comes up associated with each of the gap that you have, which is nothing but number of filled band in this language, right? So that integer number will play quite important role later on throughout this talk. Another classical problem that we can just go back to in this period, in the late 20s to the early 30s, then of course we cannot pass this Landau's important contribution, which is again solving the Schrödinger equation in the simplest form. In this particular case, he was trying to look for the solution when there is a constant magnetic field, how the electron behave under the constant magnetic field. But as we all know, The effect is basically quantizing the classical cyclotron orbits such that each of the orbits contains the integer number of multiple of the flux quanta, and that's quantization condition. As that quantization, your energy spectrum is again not continuous but discrete, called the Landau level appears, and each of the Landau level is separated by the energy amount of the cyclotron orbits frequencies, right? Now, interesting, the implication of this one is, of course, when you have the electron in the 2 dimension, applying the magnetic field, the continuous energy spectrum, the 2 dimension electron, will just kind of discretize because now you have only finite set of this integer number of the level is allowed, such that, again, that you have the once these Landau levels, and each of the Landau level associated a certain gap. Now, if my fermi level is within the gap, again, this natural numbers appears. Basically, you're asking how many Landau levels actually filled up. Now, this integer number is deeply associated with the degeneracy of each Landau level because we have to shove in this continuous state into the discrete Landau level. Each of the Landau level is heavily degenerate. In fact, you can count the number of degeneracy simply knowing that how many of this quantized orbit you just plugged in, which is related with magnetic length controlled by the magnetic field. But in the end of the day, basically knowing the electron density and knowing that this orbit size, in other words, knowing that magnetic field, you can compute number of the field Landau level simply just combining this electron density with the magnetic length. Again, this dimensionless number is what we call so-called the filling fraction. And this filling fraction, which is an integer number, plays an extremely important role that when you try to understand any quantization motion of the electrons under the magnetic field, such as quantum effect. Right?
And in both formulas, this is the 2-dimensional bits.
This one is 2 dimensions, but the Bloch theorem, of course, can applicable in the even 3 dimension, 1 dimension, doesn't matter, right? Because the important part is that when you have the discrete energy levels and when you put the Fermi levels in between the discrete level at the energy gap, you always have a set of the number of field band, and simply then you count how many electrons per unit cell you have.
But in your formula, wasn't A an area?
It is area, but it can be volume, it can be length, depends on the dimensions, right?
So this is 2 dimensions.
This let's see that no, I think it can be, if it is a 3 dimension, this area, this A is volume. If it is 1 dimension, this is a length, right? And then you have to use a density.
I was confused by
Sorry,
the A.
yeah.
You're saying it could be V.
Right. Yes. Right.
A.
But
it's 1 over N.
Right. But of course, in this talk, that I'm just talking about 2 dimensions. Right. Okay. So now I just kind of introduced 2 integer numbers that I need for throughout this talk, right? Now let's go back to say 30s, and then imagine that you become you're a physicist in the 1930s. What kind of problem you want to solve next? Well, if you don't have the imagination like me, that probably one thing is you just kind of combine these problems and try to solve this one, right? So how the electron motion should look like under the constant magnetic field in the periodic electric potential. This problem, seemingly just kind of combining these 2 problems, turned out was not too easy problem to solve. There are some of the clues that people made, but one of the most, the quantitative statement was made in the Harper, this famous paper. But look at this, it was published in 1955, about 20 years, or 30 years, or 20 years later of the time, right? What Harper did is basically he simplified the problems and that applied in the 2 dimensions and tried to simplify the periodic potential in such that way that consider this square lattice simplistic the problem you can solve and only consider nearest neighbor hopping in tight binding scheme. So that's kind of one way that you can simplify the problem at the minimal level. Right? And then problem can be just kind of parameterized and following, right? Because now the magnetic field is changing, but in fact you can define dimensionless magnetic field in such a way that if you know that what is magnetic flux per unit cell, naturally you divide that with the flux quanta, and this dimensionless number B is basically a parameter that parameterizes this Hamiltonian completely. Right? And we are working on this tight binding model, means that we have the discrete set of the basis that we can just diagonalize Hamiltonian. And after you just do that, then you get set of the equations, set of the difference equations as a solution, right? And then solving this set of the difference equations, then in principle, you should be able to get the energy spectrum as a function of magnetic field, dimensionless magnetic field B. So in terms of mathematical structures here, the ones you just write down, this one is matter of you just compute the energy level here. So sounds like the problem got solved by just arriving there once you get into Harper's equations. But if you just look at this paper, actually Harper made the following interesting statement. Turns out this is very difficult to determine in detail. Energy spectrum is very difficult to determine in detail. And the reason is that basically level structure will consist of irregular groups regularly repeated. I think this is a rather enigmatic statement that Harper made, right? What does it mean by something is regularly spaced, irregularly repeated? In fact, the reason that he made this statement is following. Because here is the famous problem of commensuration and incommensuration problem. In fact, this problem has a two different length scale. Of course, the one of the length scale is a lattice, which actually give a periodicity of the electric potentials. And the other length scale is magnetic length, basically give you, in some sense, periodicity under the magnetic field, right? Now, if these two length scale commensurated, problem might be easily solved. But what if they just incommensurate? But of course, even for the commensuration case, nearby each of the commensuration, there's incommensurations happen, right? So this commensurability and incommensurability basically make these things rather complicated. One kind of experimentalist demonstration of that issue is following toy, right? So this spherograph, in fact, consists of the two gears or multiple gears. Because of there's gears, then finite number of the tooth. So eventually, if I know that the radius of this one or number of the tooth, basically rotating this one, I can make the complicated pattern, but they will be periodic. And in terms of periodicity related with what is the number of the tooth around this, the inner gears and outer gears, right? But think about it. What if that indeed there is no gear, but if this the ratio between two radius is not the rational number, but irrational number, then of course this pattern will not come back, right? But if this irrational number is close to some of the rational number, there is some sort of quasi-periodicity you can expect, right? In some sense, this is one way you can create it fractal, right? So basically, the problems that Harper's equation contains basically this type of the commensurability issue, right? So that's where the complication or intriguing the fact comes around. So the progress need to be wait another probably 20 years or so. Then when another person's name comes in, Hofstadter, the Douglas Hofstadter. He was a graduate student under the Wannier who actually tried to solve these Harper's equations back then. And then came up with a kind of interesting solution of this problem. So look at these Harper's equations, at least one can state the following statement. If there is a commensuration between magnetic lengths and the lattice, and if these two lengths got commensurated, at least we can state the following mathematical statement. Basically, if I just make this the unit cell size big enough such that magnetic field periodicity can match in there, then basically your unit cell becomes bigger. In other words, that your Brillouin zone in the K-space becomes smaller, but nevertheless problem can be solved. If you just look at that, basically this problem states following way that each of the Landau level under the magnetic field will start to break it off in terms of the Q subband that has a p-fold symmetry, where the P and Q is nothing but just when you just replace this dimensionless magnetic field with these rational numbers where numerator is P and denominator is Q.
So they're integer. That's the point.
Yeah, that's integer. So when there is commensuration, basically, right. So basically you can state this one, right? So you can understand. But this statement get into immediate problem, right? What if the B is irrational number, but sufficiently close to P over Q, right? How you can treat this problem? It's basically that very analogous issue with the spherograph that I just mentioned, right? And that's actually not a too easy problem. What Hofstadter did is just use 70s computing power just available back then and decide rather than just look at all this mathematical solution, what if we just kind of plot out the energy spectrum with sufficiently large P and Q number, right? And that's what he did. And here is that the spectrum appears in his paper that published in 76, right? So here is energy spectrum, and here is magnetic field, basically the flux, or this you can view as a view, B, right? And he just plotted out with this one by basically solving this equation where B is something like the 49 over the 51 or some of these large numbers, and just kind of plot it out in this way, right?
Each vertical position, you draw a horizontal line, and that tells you the band structure.
Right.
With the parameter, which is the vertical.
Right.
direction.
Yes. I will just get back to the point. But this is kind of direct kind of things. Now, one thing you notice that here is this is an interesting pattern. Pattern itself. Forget about the spectrum, but just look at the pattern for now. This pattern called the Hofstadter's butterfly, later named in that way. Well, you may see that this is a butterfly like the shapes, or maybe some people call it Hofstadter's bat, moth, but doesn't matter. But actually, interesting part here is that in fact, inside of this butterfly's wing, there's some self-repetitions there, right? If you look at it carefully, there's another butterfly, and inside the wing, there's a butterfly. In fact, if you just zoom in there, very similar patterns reappears. Basically, that's the signature of the fractal in the modern language. Back then, in fact, in the 76, there was no terms called the fractal coined yet. So this is one of the rare examples. In fact, the fractal appears in quantum spectrum. And that's why it becomes kind of important. Now, so besides of this kind of the fractalness, that the important part is how we can actually understand the structures in there. Of course, a fractal, one of the things is, well, it's complicated, right? Or complex system. But there must be some mathematical structures we can find in there. So let's kind of take a look at a little bit more detail. Now I just present that the same pattern, 90 degree rotated. In a sense, I want to present in terms of the spectrum. As usual, this is then energy axis, and this is a magnetic field axis, or normalized magnetic field, right? Now, remember this is tight binding model. So zero magnetic field, you expect just one band, right? So basically, here is band bottom, and here is band top. So that's basically continuous spectrum. Simply because we don't have enough resolution, that's why it looks discontinuous, this stop here. If you continue this, basically you expect just one continuous band is expected, right? And if you just look in that way, now I can see that why there's something's coming out from bottom over here and bottom of this band. That's basically Landau level, right? If you have the magnetic field turns on, at the bottom of the band, you start to develop the Landau levels. Landau levels start to fan out from bottom, right? If I understand in that way, well, maybe this is the lowest Landau level that comes out, but then it started breaking off. And this breaking off is nothing but I just mentioned briefly that when electron cyclotron orbit becomes smaller and smaller, electrons start to see that the effect of the lattice, and the lattice perturbation becomes important, and that's why this Landau level, originally degenerated, start to break up to turn into this pattern. So in a sense, everything you see in this side is a fan out from this first, the lowest Landau level due to the breaking of this degeneracy coming from the periodic lattice potential. Right, so you can view in this way. Now here comes kind of important clue that while the Hofstadter left the field after generating this picture, it took it over by his advisor Wannier, and the Wannier tried to look at what is the mathematical structures embedded in the spectrum. So you notice that, well, this is one Landau level breaking off, the other Landau level breaking off in this way. So the one way it took that is there any invariance between this level to the Landau levels that you just have without any lattice perturbation? Of course there is. Basically, number of the states here is about the same. So idea is, instead of your focus on the energy to the magnetic field, what if I just kind of focus on number of the field electrons? That's actually equal to the number of the states in the one part of the state. So what Wannier decided to draw is, instead of the energy spectrum, what if I just kind of draw the density, electron density normalized per unit cell as a function of this magnetic field. But then, here, in the white region, that where I have the gap of the first Landau level, in terms of the corresponding the line that I can draw here, is some simply line. Just follow this like the Landau level, right? Well, nothing profound at this point. But if I just do the same exercise for the next Landau level and second and third Landau level, of course in the energy scale I have to carefully trace where is the second Landau level actually separate from third Landau level and so on, right? But if you just plot the same thing corresponding the density, normalized density as a function of magnetic field, that's simply again just a line, because the density, number of the line here and number of the states here is not changing from just a Landau level to this part of the states, right? Once you do this, you can actually do the following things. So for in this side, well, basically these are, in some sense, you can view like the whole like the Landau level. So those kind of states is corresponding again the set of this line. Now this picture is symmetric because in tight binding scheme, basically if you put the one flux quanta or integer number of flux quanta to the unit cell, everything reset. In that regard, here basically this line is basically applying the magnetic field in opposite direction. So that's it, right? So you can just do the same things, and then you get another set of the lines corresponding here, right? So what I'm stating here is basically there's some sort of duality. Here the energy spectrum, which is rather complicated, is corresponding at least a set of the line in terms of the density as a function of the magnetic field, normalized, right? And also note that here, this one is nothing but just counting the number, right? So interesting feature of this one is once you just plot it out, the slope and the intercept, y-intercept, which actually determine this line, is all the integer number because of our setting, right? What I'm saying here is that basically this line, all these things can be represented by simply the slope consists of the integer and the offset consists of integer. Two integer number appears naturally here, right? And that two integer number is nothing but again just reading off from this diagram with slope and offset, right? So that's what Wannier actually noticed. There's important the integer structures contained there. Now, looping back to our original slide, basically this integer number again, as you can imagine, tied with the integer number appears in the Bloch band, right? Especially this one, S number, and T, of course, is related with integer number appears in the Landau level. So in a sense, it's naturally expected, two integer numbers is expected appears in the spectrum, right? I know this one is quite mathematical, and you wonder that, hey, this guy is an ignorant experimentalist. Why actually he is talking about this one? I'm talking about this one, not both that I understand this one, but because of this one is extremely relevant in the experiments. And this experimental relevance actually comes after few years after this discovery about the structures of these spectrums, as well as the meaning, as well as the existence of two integer number. It comes from actually mostly experimentalists. The first thing, as I mentioned, that there are two integer number, one S number, which is offset, is nothing but how many band got filled up. So you can actually take that band, the same tokens that then you can get these S numbers out. So that's in a sense related with the band filling. But the important part is those kind of slope, T. That T number turns out earlier work that was Streda in connection with the experimental discovery of the quantum Moire effect. Turns out this T number is actually experimental observable, that especially when you measure Hall measurement in the system, you can quickly see that Hall measurement is related with the quantum conductance times of this T, which actually appears in this diagram. In other words, indicating that two-dimensional system, you expect that this whole conductance is quantized in terms of this integer multiple of E square of H, right? So that's actually one of the proof that why the quantum Moire effect do exist, that done by the Streda. About the same time, another important actually meaning appears. Actually, in the modern language, this is even more important. Not only this is experimental observable, actually this experimental observable T number is associated with the deep nature of the electron wave functions. So it's Dowlis and his co-works worked at TKNN, known as the TKNN, about the same time published in 1982, showing that not only this whole conductance is quantized, it is related with wave function structures, especially wave functions, this weird type of the derivatives integrate over, in the case Brilliant zone. Basically, back to the relay this T number. In the modern language, basically this is a Chern number associated with the wave function in the Brilliant zone. In other words, this T number as well as S number, it has some topological meaning, the associated wave function structures in the Brilliant zone. So that's basically kind of full connections made onto this two integer number that I was talking about. Practically what can happen here is following though. So if you just look at this, the band structures or the spectrums, basically whenever you have the gap, there are two integer numbers associated, especially that there's an integer number T is associated with experimental observers such as Hall effect. So if I just assign each of the gap, the white region of the spectrum I showed you before, and tells that that's correspond to a certain integer number, I pick up the color for the gap, and then in fact actually I can even color the butterfly spectrum such a way every region that I had a gap I can associate with the integer number related with this quantized Hall effect, right? And that's correspond this color, then my butterfly actually acquire even colors, beautiful color, right? Because it's aesthetically kind of quite beautiful, many physicists, experimentalists, after this kind of statement, try to look for this butterfly. And one of the men is also sitting here. Now, of course, how we can actually chase this one? Well, the experiment is in a sense simple. What you need is periodic electric potentials and applying the magnetic field. In a sense, any atomic system has a periodicity in crystal, so it's got kind of good candidate. But you get into the immediate problems there. The immediate problem is in the real experiments, you work on the finite temperature with the disorder, so the spectrum start to blur it out, right? To get the enough statements such that you have enough the symmetry breaking, you have to bring yourself out quite high in terms of the magnetic field. How high magnetic field I need? Well, maybe I need about the magnetic field where that the probably fraction of the flux quanta should fit up this unit cell. Now, if you just put the real numbers and using the atomic unit cells and so on, they quickly realize if you have the real atom, basically you're hopeless. The magnetic field you need is very easily about, say, close to 10,000 Tesla, which is a kind of basically unattainable field in the crust of Earth, right? Basically, this is a problem that unless you make this unit cell becomes large, that's not easy to realize. In fact, that was already mentioned in Hofstadter's original paper. He realized that, well, so atomic cell is impossible, but at least if you make some of the synthetic two-dimensional lattice, such that the periodicity is something like the 10, 100 nanometer, maybe you can just realize this type of problem, right? So experiments need to be wait another probably 10 or 20 years to be realized such that technology got evolved so that we can make structures something like the range of the 10 to 100 nanometers, right? So throughout the 90s and probably up to the 2000s, people try to make these periodic structures in various different ways. One way is you can just directly try to make this two-dimensional electron gas and make the holes like this, or the sum of the gauge structures. And throughout there, that you can start to bring some of the mild periodicity in the systems. And because of that, initial Landau levels start to break these symmetries and make some of the oscillation in the magnetic conductance and Hall voltages and so on. So we know that perturbation works and Landau level breaks down. So that's actually a minimal step. But to really show that we have this fractal spectrum there, either you have to do the energy spectroscopy, or at least you have to show that there are two integer numbers governing this type of spectrum. And that was not easy. Part of the reason is whenever you just do the sum of the fabrication, basically you start to spoil your two-dimensional electron gas. That even you start with the highest quality. Another method was done also in the Princeton, for example, that instead of you using this kind of artificial structures that lithographically define, you may use a dipole copolymers and try to introduce some of this periodicity. But there's always kind of finite tunability between two-dimensional electron gas to the whatever things you structured in. Make this experimental proof was extremely difficult. So there comes graphene stories. Basically, what graphene brings is kind of two different directions. One is, of course, graphene is two-dimensional system. It's one single atomic layer of carbons. One can get the extremely high quality nowadays. It has kind of unique dispersion relation where that, especially near Dirac point, near this charge unity point, spectrum is linear, and some people call this is quasi-relativistic spectrum. But anyway, because of this spectrum, interesting spectrum, when you apply the magnetic field, you get this the Landau level forms out of so-called Dirac spectrum, such that at least if you get into this lowest Landau level, the separation of the Landau level is very, very large. Because of this Dirac spectrum nature, therefore, the quantum Moire effect in graphene is rather robust. Paul mentioned that the quantum Hall effect is now even being seen in the room temperature. Part of the reason is because of the Landau level separation is such a large, with even 10 Tesla, the gap here is many, many times larger than the energy level and energy scale of the room temperature. So that's another kind of important part. So you can see the quantum Hall effect with relatively readily, and the gap of this quantum Hall is large, such that you can actually bring somewhat robust the quantum Hall effect in the system. But on the top of that, there is yet another very intriguing part that we can introduce. Now, of course, you can pattern graphene and try to incorporate the, again, periodic electric potentials. But then very similar problems appears, like what I state for the two-dimensional electron system in semiconductor interface. If you just do the fabrication, you tend to degrade the sample. Electrons start to see more of the disorder before you see the periodic potentials. Is there a better way that we can incorporate periodic potentials? In fact, there is. Actually, nature provides us the very neat way. That's basically using the cousin of the graphene. So graphene, we know that it has a kind of this honeycomb-like the structures. Actually, nature provides us very similar materials called the boron nitride, where basically 2 carbon atom in a cell is replaced by boron and nitrogen. Because they have the ionicity, so the nitrogen has more electron, boron has less electron. Basically, it's ionic bond, close ionic bond, means that these structures do exist, but it's more like the insulating states. However, like the graphene, there is no chemical bond going outside of this layer, which means this is a layered system. Like the graphene, you can extract it as down to a single layer, and moreover, they don't interact strongly with whatever things are outside or whatever things are on the top or bottom. So van der Waals interaction is only weak interaction they provide, which is very good because that they can serve as a really good substrate for the graphene. Indeed, past a few years at Columbia University, throughout the collaboration I mentioned, now we know how to deal with the graphene as well as boron nitride. Unlike the expectation for, by the way, we still use Scotch tape because that's still the best way. You get the highest quality sample. Now we use actually Scotch tape not only once, here twice, because we have to take the boron nitride out and we have to take the graphene out. Difference is, of course, it's slightly more complicated than Scotch tape. We use polymer layers and control this, a little bit better control. But essentially, this is still Scotch tape method, but you just do twice, but well-controlled way under the microscope, and then you can actually stack them together. So basically, that's a way. But once you stack them together, turns out they make the device onto the graphene sitting on the boron nitride. Quality of the graphene sitting on the boron nitride is extremely, extremely good. Basically, you can maintain electron mean free path now up to something like that over 10 micron. So it's an extremely good sample you can create. And that's actually one immediate kind of important part, such that we can still maintain extremely long mean free path of the electron. But the most relevant part of my talk is there are many different ways that we can actually stack the graphene onto the boron nitride. Both of the lattice has a 2% of the lattice mismatch. So even if I just have the boron nitride, put down the graphene on the top, there is some mismatches. So even if I match here, there are some mismatches there. Now even worse, because this one is stacking just with some random rotation, orientation. So therefore, there is some chance that they actually sit into the different angles like this, right? And there are many different cases. I can just make them, right? Depends on how you stack. So I just kind of put them here, that different cases with 5 degree, 10 degree, 15 degree, 20 degree, and 30 degree. It looks like a mess. But if you just look at from the back, you start to actually pick up some pattern, right? Here is some sort of patterns appears, periodicity, and here's periodicity. And the periodicity, super periodicity, becomes smaller. And this is what we call the Moire pattern. Basically, when you have the two similar patterns, close, kind of overlap together with some mismatching angle, there's basically some superpotentials, the modulation appears. Of course, this is a mild modulation in a sense because it's based on the van der Waals interactions, but nevertheless, this is one way you can create the periodicity beyond this atomic length scale. And this periodicity, in principle, can be controlled by just kind of adjusting that angle of the lattice sitting together. So the periodicity, the superlattice length scale, is controlled by basically this mismatching angle that you have.
Aren't there some angles that there's no periodicity?
I guess that the any of the swing, in principle, there is no true periodicity, right? So Moire periodicity is just the grand modulations. But if you just look at all the atomic detail, they don't then they cannot match each other, right?
Yeah.
Right. So, but nevertheless, what we need is just a long wavelength gradual modulation. So this actually is a good serve. Not only you can just create this in the PowerPoint, in fact, actually this is readily happen. Many of the STM study already happens in other places. It shows that when you put the graphene on the top of the boron nitride, STM can start to pick up this all different periodicity, long wavelength modulation in that on the top of the atomic scale image of the graphene on the boron nitride. So they do exist. Not only that, if you just do the careful STS spectroscopy studies of the STM, they do start to pick up the spectrum actually contains some anomalies at the high energy. In fact, this is expected. So think about that this is part of my spectrums there, right? If you just add this periodicity, what happens is basically that will make the Brilliant zone smaller, right? If you just consider this periodicity of the Moire, right? At the end of the Brilliant zone, if you turn on the small interactions between the two lattice, basically will break up the gap. Basically, that's Bloch theorem, right? So this spectrum will break it off into the sum of this mini gap due to this interaction of the Moire, and basically STM spectroscopy pick up the position of this gap opens for the electron side and hole side, so they know that this is really kind of create some of the effect. In fact, if you know that this energy scales with this length scale, they have the good match. So we know that indeed this Moire superlattice can open up this mini gap, and that's important because at least this one gives us the Bloch type of the quantization, Bloch type of the gap appearing in this system. Now, if you have this type of system, graphene sitting on the boron nitride in the right angle, or just kind of about the right angle so that we can experimentally accessible, something like this, using the AFM, you can see that this periodicity. So I know that what is this superlattice, the periodicity. And if you just do the transport measurement, basically hook up the wires and measure the conductivity, you can see that indeed the transport can pick up the signature of those kind of mini gap appears. Normally that you have the central peak appears at the Dirac point and that's it. But when you have this superlattice, Moire superlattice, there's a small peak appears. And in fact, if you just measure the whole measurement across that peak, basically your whole voltage shows a sign reversal, indicating that basically, indeed, we have this kind of band gap opens up, so that carrier sign actually reverse there, as expected that this superlattice, the band gap appears in the spectrum. So transport data indicating indeed there is the small mini gap opens up such that you have the electron like the gap, whole, the one band, two band, the one band here break here at this point, right? Okay, so this is a really kind of tantalizing the evidence that we have this Moire superlattice induced gap opens up. Now, how can we prove that indeed there is this Hofstadter spectrums in here? Now, for that, we need to go to the high magnetic field such that we can induce Landau quantization. So we did. So we apply the high enough magnetic field, and we changed the gate voltage. Here, the gate voltage basically changed the density or fermion level, and plotted out both Rxx, basically longitudinal resistance, and Rxy, which is a transverse resistance, basically voltage, the whole voltage divided by current in the resistance unit, shows kind of these plots, right? What you see here is a lot of fan. Fan means that, well, there's a lines comes out from the zero gate voltage correspond to zero density, there are lines comes around. This line comes out from this origin is what you call the Landau fan diagram. Often it's quite important to understand the quantization effect. And you see that this black part is where that basically that your Rxx longitudinal resistance is suppressed. And interesting enough, that whenever that happens, here is the band appears, in other words, constant of the Rxy, quantization of the Rxy, in other words, shows up. That's basically nothing but quantum artifact. So in the approximate way that you see that more like what you expected in quantum artifact. But on the top of that, there are some of the new feature appears. For example, here is some of the line does not necessarily comes from this point. Some of the line comes from where that this the mini peaks appears there at the mini Brillouin zone boundary correspondence here, right? Not only that, if you just look at this, the whole conductance, there is some of the structures appears in the constant magnetic field in certain location. So some of the small deviations there. If you just look at the a little bit more detail, those kind of feature becomes even clearer. But they look like this. Still, I have the basically Landau fan here. But what I'm going to tell you today here is this is the ultimate evidence that I can present the Hofstadter spectrum. You may say that I don't see any butterfly. What do you mean here? So for those of you non-expert on this quantum physics, I have to actually tell you how to read off this diagram first. So let me just kind of step back and just take the kind of one step, how to read off this fan diagram and to appreciate why actually those data that I present is rather strange. I'm just showing you here the typical fan diagram of this graphene, or it doesn't matter, it can be graphene or any two-dimensional electrical system, where you can tune the density by the gate voltage and apply the magnetic field. I just show the fan upside down here in this case. So here's a zero density and zero magnetic field. What you see here is all this black line comes up. That's where that you have suppress of the RXX. Now, signature of the quantum effect always appears experimentally as the suppression of the RXX. RXX goes to 0 while the RXY shows some quantization. Right? Now you see that this RXX goes to 0 through the sum of the line, like the fan. Why there's kind of fan like the line? Well, that's because of the Landau quantization I was talking about, right? Because of this across the line, basically you have the constant filling fraction means that across this line, certain Landau level is fixed, the field up. Right? So you are in the gap of in between the Landau level when you just put the magnetic field and density correspond to this line. And the slope, which actually naturally the integer number, is nothing but filling fraction. Right? And this filling fraction is important, not only chase through this line, but because when you just look at the RXY, which is quantized, that quantization is immediately related with that filling fraction number. Right? So one integer number governs everything in quantum effect, right? That's why that the people just study about quantum physics, they are kind of so much interested in the filling fractions, right? Because it tells everything in this diagram, right? So arming with that idea, let's go back to the spectrum, the data that I showed you, right? What I just showed you here is RXX again, that same plots, right? Let me just cut through the one of the constant magnetic field and shows both the corresponding RXX and RXY at the same plot, right? As I said, I crossed many of these zero lines appears here. RXX goes to 0, and whenever RXX goes to 0, there's a plot, the flat plateau appears in the RXY, showing that this is nothing but quantum effect I just state, right? And for the quantum effect, the filling fraction is important, and filling fraction can be obtained simply at the constant magnetic field, then divided by the density. So I know that the gate voltage can be converted in terms of the filling fraction at constant magnetic field. And seems like they're working, right? If you just look at this, basically here that when the filling fraction is 2, I get the 0, corresponding the plateau value appears here, the integer number in the 2 denominator. Here's the filling fraction 4. The 4 appears in the plateau value in the denominator. So it seems like it's working. However, that argument doesn't work in this side, right? Basically, that I have the 4 filling fraction, indeed I have plateau, but that plateau extended up to the 3 or 1, and there's a plateau appears not corresponding to any of the integer number of the filling fraction. Basically, if you just look at this side, filling fraction cannot explain the quantum effect I'm getting here. And incidentally, that's actually location where I have the fan not passing through the 0, right? But this is precisely the point of the Hofstadter spectrum. Remember that in the Hofstadter spectrum, I need a 2 integer number rather than 1 integer number. So that's why with just 1 integer number, I cannot explain the spectrum here, right? But then the next level of the question is, how can I find this 2 integer number in this plot? Indeed, 2 integer number is nothing but just the slope and the offset in so-called the Wannier diagram, density versus the magnetic field. Well, here, this is magnetic field, this is the density, what I need is I just can normalize the density and the magnetic field in terms of the density per unit cell and magnetic flux per unit cell. Then I should be able to redraw this in terms of Wannier fashions, right? Because I know that what is the unit cell size of this Moire pattern from AFMs or from this other indirect measurement, I should be able to do that. So that's actually this plot. I just kind of take the data and replot it in terms of the normalized density and normalized magnetic field. Well, there are many features here, but all the features, if you just follow through, basically you can do the following things. They all fall into the lines where the slope and the offset correspond to integers. So I can just kind of pick up all this integer number by just looking at this diagram. You may say that, well, there are a lot of features and you draw a lot of lines. Some of the feature may align with some of the lines, right? But statement is much stronger than that, right? What I mean here is basically, if I have the corresponding data on the RxY, these plateau values, right? If I just have the plateau, whenever this hits this dark region, that is showing the quantization, and the quantization number can be picked up from this plot by just looking at the slope of this line. So it is much more stronger statement that I can have, right? Let me just show another demonstration. I just kind of zoom up some of the small area of this the diagram that I showed in different color. There are a lot of features, and I just said there are a lot of features can be explained by just again drawing the line, which actually this line is not arbitrary line, but line such that has an integer slope and integer offset. I can just explain all of the features in diagram, right? But when I said that I can explain all of feature means the following things, right? Pick up just kind of these two features. There's a dark strips here. Basically, I have complete suppression of the RxX that corresponding to this plateau like the region appears in the RxY. Not only that, if I just cut through my plot along this RxY, basically, whenever that RxX is 0, that basically plateau appears, and this plateau value is corresponding slope of this one, right? So all of the lines I showed you, in fact, it does that. So this is not arbitrary line that we can draw, right? And then we can exactly pick up this two integer number from the data.
Sorry, but that island, the yellow island that was on the plot, has any meaning?
This one?
Not the other one, the smaller one, down in the lower left corner.
Oh, this one. Yeah, okay, so this one is an interesting line because it's not, let's see, do I have if you look at that, that doesn't correspond to 0 of this line. This is probably coming from one of the density of state peaks, and this is nothing to do with the quantization. So it is more like the complicated band structure effect in the middle of the band rather than this Hofstadter spectrums I'm just talking about. So this is kind of big features, but not correspond to one of the lines that I just draw, right? I just kind of draw the line only when I see that RxX goes to 0. Actually, story goes even more, right? Again, that I'm just showing here the RxY, sigma xy. I mentioned that there's a features that corresponding to some of the horizontal line in some magnetic field. Now, if I just plot that figures in terms of this normalized flux, in fact, that line is just corresponding to the half, third, fourth, and fifth of some of the simple integer. Whenever I have this simple integer, basically there's sign reversal happens in the whole conductance. In fact, that's where exactly expected. If you look at this Hofstadter spectrum, whenever the magnetic field is a simple integer like this, that's where you expect continuous band appears. But this is a weird band because it is continuous band because there is a commensuration, but right above and right below this band, there's a maximal incommensuration happens, which means basically this is band, continuous band, but measure 0, and right above, right below, there's a maximal discreteness appears. What is the net result? Across that band, basically, there's a crazy things happening in the whole conductivity. Basically, whole conductivity shows a lot of fluctuation and sudden change of the sign. Basically, that's what we are going to see that across this fractal band, so-called fractal band across this band. In fact, if I just plot it out, cut through this constant density at the changing magnetic field, plotting out both sigma xy and sigma xx. Sigma xx here is the more or less corresponding density of state. In fact, whenever I cross this fractal band, it's picked up, showing that there is enough density of state. But whenever that happens, sign reversal happens for the sigma xy, showing that band nature change from electron to hole, which is again expected. But more crazy thing is, if you just look at it carefully, there is some fluctuation, look like things appears in the sigma xy. But if you just look at it, zoom in, those kinds of features. In fact, those small features are corresponding again, mini quantum Hall effect appears there. So in some sense, quantum Hall effect itself is appearing here in the recursive way that really kind of falling down the kind of closed loop that indeed we are seeing some of the recursive features, which is basically essence of the fractalness of the spectrum. Well, you may say that this might be the kind of important kind of signature, but you may say that, well, I don't still see the butterfly, because in a sense, this is transport measurement. We are not sensitively determining the energy spectrum itself, but we are actually measuring the whole conductivity, right? So for me, it is very difficult to present the butterfly, but at least in this transport measurement, we can pick up those quantized integer numbers out of our experiments. Shows kind of really dualities there. I'm sure that once you start to use the spectroscopy tools, you may be able to see that those kind of butterflies like the spectrums or self-similar spectrums in there. But in some sense, this is an even stronger statement we can make in the experiment that we have two integer number that embed into the spectrum. Now, it poses actually even great challenges. Up to here, I would say that we solved, say, 37 years old problems that when Hofstadter first showed the spectrum, at least we can show that we can find these two integer numbers. But actually, experiment goes even beyond that. All of this, the gap that I measured, the quantum Hall state, I can say the fractal quantum Hall state, in a sense, it is governed by the two integer number in the fractal spectrum. In fact, if you just measure the gap of some of them, we cannot do all of them by just looking at the temperature dependence measurement, we start to see that certain gap is much, much larger than expected. For example, under the magnetic field we don't expect spin degeneracy is breaking strongly. But the spectrum we have shows spin degeneracy is completely broken, and the gap is much, much larger than just what we expect in the Bayer-Zeeman splitting, which means that somehow electron-electron interactions plays a really important role to create some of the quantum Hall ferromagnets driven by the electron-electron interactions. In fact, it's actually go even beyond that. You can ask that, what is the ultimate effect of electron-electron interactions with this type of the fractal spectrum? Indeed, quite a recent measurement we have, let me just skip all of this thing because I don't have time. We start to see that not only we see that this fractalized spectrum, again, that beautifully show up all these kind of things that I just explained, but they actually now start to live with fractional quantum Hall effect in sufficiently clean sample. We have strong evidence that sample can support both fractional quantum Hall effect as well as its fractal spectrum. Now, evidence we don't have yet enough magnetic field to look at that. Seems like all this fractional quantum Hall effect we see that in this 1/3 series actually strongly influenced by this fractal-like nature that I was just talking about. We don't yet know that what is really happening here. But here's a really important challenge for any theorists sitting in here that are interested about this one. I told you that in single particle picture, to understand this fractalized spectrum, need a two integer number. What if that you just try to explain the fractional quantum Hall effect appears in the fractal spectrum? How many numbers do you need? Do you need a two integer number, three integer number, four? It's not obvious at this point. What do we need to understand those kind of things? But experimental is really coming up. It's a really kind of around the corner to tell you the experimental answer. Okay, I think that's all probably I want to say today, but basically what I want to tell you is with the graphene, we can actually have still a lot of fun that we can enjoy to solve many interesting physics problems. Thank you very much.
Where do you get a 35 Tesla
So, okay, so we have to go to the Florida. There is a National High Field Magnet Labs there. So this experiment was done at the 35 Tesla. And we regret that we should have recast the 45 Tesla there as a big magnet, hybrid magnet can go to the 45 Tesla because the reason that I cannot give you answer today why I need whether 3 integer to 4 integer and the fraction is basically I need a little bit more higher magnetic field that this whether this one really shows some slopes, the enough slope that associate with the quantization. We basically
Why don't you just go to higher field then?
let me tell you that 35 Tesla magnets to use this one up to this level with this level of the experiments sometimes need about 10% of the power that City of the Tallahassee use. Right, so this is a very expensive experiment in some sense. 45 Tesla magnets are really, it's available, but there are a lot of applications. So you have to wait some time to hope on that magnets. So sooner or later, I'm sure that we can go for the 45 Tesla and get a little bit better answer. But at this point, our answer is just to stop here. Yeah. Yeah.
In terms of the Moire patterns, can you control the angles to control the periodicities, or is it basically by chance that you get it?
So in principle, yes. So we can just carefully try to align them in the certain angles. In practice, it's rather difficult. The part of the reason is that you can get the high angle of the Moire, then basically your Moire periodicity actually is small, and which means that you have to go to even higher magnetic field. So we want to have that kind of relatively large angle, small angle, such that the periodicity is large. And the angle that we need is about 1 or 2 degrees. So there, that basically it's not easy to just control. So at this point, we just rely on the luck. Sometimes we get the right size, and then we just do the experiment.
Did you show in your little inset what the spectrum looked like for the Hofstadter for the hexagonal lattice? Is that what that was?
Okay, so that's a good point. So the Hofstadter spectrum is basically seeing in the spectrum I just showed you is a square lattice. And of course, if you change it to the triangular lattice, spectrum itself is different, looks different shapes. So, right. So in a sense that the Hofstadter spectrum itself is not directly associated with this one. Our theory is that the role of the theorist is calculate this one for this hexagonal lattice. More precisely, it is honeycomb lattice. They did that. But the important part is those existence of 2 integer number is generic. It doesn't matter whether it's a kind of whatever symmetry it is, right? 2 integer number always appears because it's coming from Landau quantization versus the Bloch quantizations. The only difference is because of the energy level is different. So
I just wanted to see where you were on that diagram.
Nowhere in the diagrams, because what I'm trying to say here is that some line is solid and some line is the dashed. Dashed part is basically this is a smaller gap than other things, so it doesn't show up, right? So what happens is if you change the spectrum from square to the triangles and so on, what happens is in this Wannier diagram, which is the dual of the energy spectrum, you basically have I have the turn on here, turn off, and turn back on here. Those kind of region that where it's turned on in this diagram is determined by detail of the spectrum, right? So basically, this diagram cannot be directly compared to the spectrum in a sense. Because
the spectrum even of the honeycomb.
Yeah. So this diagram can be read off in each of the different symmetry. Let me put it this way. And then you can find out, hey, so where is my gap? Opens up the corresponding this number, right? So I don't have the spectrum with this slide, but I can show you the spectrum. And spectrum is actually quite different from this butterfly. It doesn't look like butterfly, but there's a self-similarities, right? And that self-similarity is governed by this integer number, right?
On the lower left, at about 0.2 and -4, I see some lines that sort of slope gradually. Look at the bound on the edge, the numbers on the edge. 0.2 on the left side, go down, down,
Point.
down, down, stop.
In the scale.
There's-
He's looking
right.
at the scale, not the
There's some lines that goes
inside.
gradually slope up to the right. Are those meaningful? No, the black lines that you didn't,
You mean this one?
yeah, but they slope the other way too.
Yeah, well, okay, so here that we may not have the enough resolution because of too low magnetic field, but, right, right.
I'm just curious whether those are significant or just noise or something.
It's not certainly the noise level, but certainly that whether you can draw the features here, that we have to zoom in a little bit more details. But we have all the data in the zoom in that I showed you, right? So note that not all the features here are significant. The significant features always appears where you have the separation of the RxX, and whenever you have the corresponding plateau in the RxY, that's only the significant features we can count on in this data. Right. There are some of the data actually shows the kind of bright strips, but that does not correspond to the minimum of the RxX and the plateau, so that cannot be captured onto the theory that I just explained today. Yeah.
Are there any shot noise measurements to support this kind of spectrum?
Not on the spectrum yet, I think, but generally shot noise measurement has been done in the graphene. And then they shows some of the interesting features that follow through the linear spectrum. Now, I'm not sure whether anybody did the shot noise measurement under the magnetic field, right? But not that I'm aware of, right?
Because this may also be relevant to the comment about many-body interaction.
Yeah, potentially, right? So I think that you may actually, so the one way is indeed, if there is an interesting diffractional quantum Moire effects that reside somewhere, then you want to kind of know that what is the excitations of the diffractional quantum Moire states, and there may be short noise measurement that can tell you about the what is the charge quantizations and those kind of issues, right? In principle, can be done, but it's a very challenging experiment at this point.
Okay, I think we can continue over the machines upstairs.
Yeah, thank you.